setting those things off? Are there alarms in each room? Smoke detectors in each room?
Yeah. The ones in Centennial, they're so sensitive that if somebody runs their bath too hot, the water vapor will actually set off.
Yeah, so that was going to be the next question. What kind of alarms? They've got, if you go looking at like fire alarms, there's different types. There's the ones that just detect the smoke, and then there's ones that do the smoke and ionized particles.
Yeah.
So like if those are in the kitchen, they'll always go off anytime you like fry food. It'll go off.
I was in Centennial for about 3 semesters. I finally moved out into an apartment. Every semester there was probably about 15, 20 fire alarms.
Yeah, 12 times so far.
You think they'd, I mean, the system I think is all hardwired in, so they should know which one went off.
They do.
And they should be fining people.
There's a little device right outside right inside of one of the entrance doors.
Yep.
That actually says like what room the alarm was set from. And,
Yeah. I remember seeing big panels, and they'd all be like green because they're ready, and then if they're going off, they flash.
I usually know what happens because like my roommate will move the panel, so that's right side of the entrance door. I go out of it and Snapchat whoever they know lives near that room. What's going on?
Oh, jeez. It's crazy. All right, well, it's 11. Let's get going. Let's get started. We're recording. It's going to go live. Monday, we'll have a quiz. It'll be on Blackboard, and we'll just start it on Monday, like first part of class. So on that quiz, it's going to cover the material for the one sample tests. So it'll be your like the material leading up to Z test and a T test. So that's just going to be what it is. I think it's just Z test or T test. And then what I plan to do is have like the sign test and the T test in R as another quiz later on in the week, probably on Wednesday. Just since you have the homework, you've done the homework, you've practiced it, these quizzes will be just kind of give you additional practice to get ready for the exam. So the exam isn't the first time that you're actually trying to do something on your own. All right, it'll be an online quiz. I think it'll be less than 10 questions, but and you'll use R to calculate your p-value and stuff. So you don't need the tables, and you're not submitting any R markdown document because I'll just ask you for like p-value or t-observed value or your z-score or whatever. So it's something that you might have to do. All right, so that'll be on Monday, and we're going to try to have some quizzes, more quizzes going into our third exam. All right, so this is where we left off. So we're talking about this idea where we have multiple groups, so 2 variables. We have a continuous variable, that's going to be our measurement variable. I guess it doesn't have to be continuous, it can be discrete as well. But some sort of measurement numeric variable. All right, and we have a second variable, which is our categorical or qualitative variable. All right, and with that qualitative variable, we're going to have 2 or more groups. When we test for significance, when we test for means or medians or variances, what we're testing is if our values all belong to one group. So if they belong to one big population, then all of their means and all of their standard deviations and variances and medians and whatnot will all be the same. Our sample statistics are used to infer the population parameters. So if we make our first assumption that they all come from the same population, then we can figure out through just random probability theory, sampling theory, how much of a range we should have in our means and so forth. So the basis of these tests, or basic question of basic question for problems like this is, are the means equal? Are they the same? Are they different? All right, we're getting at the means. So our null hypothesis in this case we make the assumption that they all come from the same population, so our null assumption is that all of our means are equal, or all of our variances are equal. That's going to be another test that we'll learn. The alternate will be at least one mean is different from the rest. Now, if we have two groups and we determine that, yeah, at least one mean differs, then we could just look at the value of those means and make that conclusion or that interpretation that one mean is larger than the other. Because if they're different, and you only have two groups, then by definition, one is going to be larger than the other. But if we have three groups, like I have depicted here, and we have at least one mean that's different from the rest, we then have to go that next step to figure out which of our means are different. Perhaps it's one, perhaps it's all of them are different. So we're going to start with the two-group situation. All right, so our categorical variable has two groups in it, and we're going to test we're going to ask the question, are the means equal? And that's the same thing as saying, do our groups come from the same population? All right, so our null hypothesis is that the means are equal. Our alternate is that the means are not equal. We could set up direction. We could have asked the question, is mean of group 1 greater than the mean of group 2? Or is the mean of group 2 greater than the mean of group 1? We can ask that, but the situation of doing that in a biological experiment is pretty low. So we're just going to focus on, are they equal or are they different? All right, so if we assume that our null hypothesis is true, we have to come up with a test statistic. In the z-test, that was our z-score. In our one sample t-test, that was our t-observed. Well, we can generate a t-observed for the two-group situation. So what our two-group situation is actually testing is the difference in our means equal to 0? That's really what it's getting at. So if we do that, then we're not really comparing two groups. We're not comparing two variables. Why not? Because we're going to subtract the means to get a new value, which is the difference. And if it's a difference, we get a single value that we can then compare to a null distribution. So we've got our difference, just like what we did before, x minus the mu. We're going to assume our difference is 0, and then we need some measure, some standard error. And that's what this is. You take our what's called our pooled variance. Our pooled variance is basically how much variation do we have in that difference, in essence. All right, and we're going to divide it by the sample size, but we have to account for the sample size of all of our groups. And when we do this transformation, incidentally, we still approximate a t-distribution, but our degrees of freedom are different. So our degrees of freedom with our one sample test was the number of samples, or the number of items in our sample minus 1. For one of these two sample tests, it's the number of our samples in each group added together minus 2. So we lose 1 for each of our group. Are we going to have to calculate this? No, we don't. We're going to use R to do this calculation for us. But you should know that our T is our test statistic. That's what we're going to use to determine if our two group means are the same. The assumptions of this test, 3 of them, and they're the same assumption that we use for the analysis of variance. It's data are random and independent, and as I've said in earlier tests, we plan for lists with our method of data collection. That's how we plan for the random and independence. Sometimes we violate that, and we can't do anything about it. So there are ways to utilize a different statistical test that accounts for that non-randomness. The example was heart rates before and after exercise. The individual gets measured twice. We obviously violate the independence because if you naturally have a high heart rate before exercise, you should have an even higher heart rate after exercise. That's a type of non-independence. So we're not going to really worry about random and independent assumption. Second assumption is that data are normally distributed within each group. And that's important. You can't say that our data are normally distributed because are you talking about all of our measurement variables normally distributed, or we're normally distributed within subsets of our data? So this is kind of what I mean. view. We have a t-test example. What we're going to do is, oops, I've got my one sample test. This will be done with that. Done with that. Let's create a new markdown document. This is, what are we on? Assumptions map. All right, so we're going to start with our t-test. This is a two-sample t-test, but we could just say t-test. Our null hypothesis for our two-sample, actually, let's put our requirements. One categorical variable with two groups only. So this is our independent variable. And then we have one measurement variable. And this can be continuous or discrete. Say one measurement, move that. Just to maintain consistency. All right, and that's going to be our dependent variable. That's our requirement. Our question with these types of tests, are the means equal? And that means then that our null hypothesis is that our x bar of group 1 is equal to x bar of group 2. And our alternate that we're going to do, we're not going to do a one-tail test. We're just going to do x bar is not equal to x bar 2. So group 1 versus group 2, null and alternate hypothesis. Our test statistic is t with df equals n1 plus n2 minus 2. So we have a -1 for each of our groups, and then we're just going to add them up. And reporting, we need our conclusion, interpretation. We need our test statistic, degrees of freedom, and p-value. All 5. I guess I should say H. Underneath our hypotheses, our assumptions. Data are random and independent. Two, data are normally distributed within each group, and that's important, that within each group. Groups have, and then our third assumption is groups have equal variance. And the term for that is homoscedastic, and it's in our presentation. So we've got that. All right. So our normality assumption. I'm going to use the third header here. We're going to generate just some data. All right. And what we're going to do is generate two groups just to demonstrate the importance of our assumption. This assumption is being normality within each group. So we're going to have our x1 group is going to be, we're going to repeat just A, and we're going to repeat it, let's say, let's do 100 times. Let's get it to be large. x2, we're going to repeat, and we're just going to call it group B, and we're going to also do that 100 times. All right? And then we're going to have y1 and y2 And we're just going to round. We're going to have, oops, sorry. We're going to round that. We're going to round it to probably 2 decimal places. But we're going to draw it from a normal distribution that we are normally distributed. So we've got 100 samples. That's going to correspond to our A group. All right. And our mean, we're going to use 15, and standard deviation is 2. And we're going to round it to 2 decimal places. And for Y2, we're going to round. We're going to create our norm vector. And again, it's going to be the mean. This time, we're going to do mean of 25 so that they're obviously different. All right. So that they're obviously different. But we're still going to have a rounding to the 2 decimal places. All right. And then what we're going to do is set up our data frame. So we'll do xdat as our example data. We're going to use data.frame. And there's a reason why we're going to be doing this. So we want, let's say, our group, let's say, what should we call that group, A and B? Give me like some sort of categorical name. How about this, grade? Grade, A and B. All right. So grade is going to be the vector. So C, and we're going to do x1 and x2. Okay, so what the C does is, remember, it creates that vector. We're going to create the vector of our x1 data and then our x2 data. So it basically stacks it on top, so we get one long vector that should be 200 data points. The first 100 will be A, the second 100 will be B. And since we use quotation marks around the A and the B, they're text. R will recognize those as text. And I think what we'll do is just do factor before that. I don't want to get an error. So we want to tell R, when we factor it, that this is actually a factor level variable. And then for our second one, so we have grade. What should this be? I don't know. We'll call it as count. And again, we're making a vector of that y1 and y2. And everyone's going to be a little bit different. I don't care, because we're just using this for the normality assumption. So when we run it, we create a data frame called xdat that has 200 observations on 2 variables. So just if we create a plot, we can plot the count as a function of grade, where the data is xdat. When I run this, we should get a box plot that looks something like this. It doesn't have to be exact, but it should be data that puts us close to 15, data that puts us close to 25. When we look at the box plot itself, our median bar is located mostly in the middle of our interquartile range. Our whiskers are approximately the same distance above and below. All right, something like that. Yours may have outliers. This one did. All right, but we have that. All right. The assumption, so with our t-test, and this also applies to ANOVA, the assumption is that data are normally distributed within each group. All right? Here's how we check. All right, here's how we check this assumption. We are going to use the QQ plot, and we are going to write our QQ plot function as a formula. Why does that work? I'm going to go back to the help document. Probably isn't going to find it. fit. Hey, it's in the car. Move this. All right. So in the QQ plot function, we use QQ plot and then a vector. And that works. All right, we can adjust everything. But a little bit farther down, it gives us this. Which means that we can pass the QQ plot function a formula. And this is new. This is new. So just say, I'm sure if you're working on your own personal computer, this will work. What we're going to do works perfectly. But if you're using a computer that's on campus, it's possible that they didn't update it to our version 4. If they didn't update it, then this isn't going to work. But all of these should be fine. So what this means is we can give it a formula, just like we do. Y is a function of x, where y is our measurement variable, x is the grouping variable, and data is the data frame where we can find x and y. Right. Now we can make subsets. So those of you taking the graduate level class, we can do subsets to check the normality assumption across groups within other groups, which is kind of the basis for two-way plus ANOVAs. All right, but we also can pass it differences in, the normality. Are we going to test normality? Are we testing t distributions and so forth? All this extra stuff can be added. But this makes it a whole lot easier because instead of pulling out individual groups and testing normality of the individual groups, we can utilize our QQ plot function all in a single step. So I can run QQ plot. We're looking at count as a function of grade, where the data, where count and grade are found in xstat. Now, I know this isn't going to work because why? We've got to load our libraries. So I'm going to load library car. And now once I've loaded it, we will see, once it's loaded, we'll see that this works. This is pretty cool. It generates our QQ plot for group A, and it automatically generates a group plot for grade B. This is a whole lot easier than using the subset function to pull out all individuals of group A and then doing a QQ plot. Downside to this method is that the graphs tend to be smaller, and if you have a bunch of groups, they tend to be harder to determine if they are normally distributed. But I think here I can see enough of the data points and enough of the figure to make a conclusion. So are we normally distributed within each group? Yeah, so what that is saying is our measurement data, count data, is that normally distributed within group A? And then it goes to that next step and says, is it normally distributed within group B? That's our assumption. So our interpretation here is that count is normally distributed within groups A and B. And that is our assumption. Our assumption is not count is normally distributed. And we would not test our assumption by doing this. QQ plot xstat $count, where we ignore the groups, because then, so I'll leave that up, get this made so we can actually look at this QQ plot and discuss it. This is xstat $count. This is how we've been how we were checking normality of some of our other variables. We don't do that for here, because if you do that, you get something like this. Is count normally distributed? No, clearly it's not. We're not inside the envelope at all. And then the question is, why isn't it? Now scroll back. Why isn't this normally distributed? It's normally distributed in grade A, and it's normally distributed in grade B. Why isn't this one normally distributed?
Because it's taking into consideration both groups.
It takes both groups, and where's our mean located in both groups? One's at 15, one's at 25. So, you know, when you do that QQ plot, just quick review, and it's small. It takes our distribution and plots quantiles. It says this is our expected quantile from a normal distribution. This is the quantile of our actual data. So we're dealing with the distribution, or we were dealing with the distribution that looks like this. In this data set, we have two clear groups. And we get something like this, where that's group A, that's group B. But how I made this figure, it's trying to make a curve that looks like that, and clearly that's not the case. So even though each individual group is normally distributed, the entire variable is not, because we're bimodal. And that's what's going to happen. That's why our assumption isn't that this variable is normally distributed. Our assumption is that it's normally distributed for each group. All right? Good with that? So we have to look at normal distribution within each group in our data set. Our third assumption is variances if the groups are equal. All right, so, and we're going to learn how to test that. And that's the reason this variances if the group are equal, we make that assumption, is we will simplify how we calculate this term, this pooled sample standard deviation. If we are not equal, we don't need to make this assumption. We can actually calculate the standard error while accounting for unequal variances. So I just did that example data so we can look at the normality assumption. I wanted it to be clear that our assumption is normally distributed within each of our groups. So our t-test example that we're going to work through is this. It's t-test example CSV. We're going to read it in as EX1. And what this data represents is plant heights. So we have two experiments that we run. Or we run two experiments. And for each experiment, we have a different different condition. And our question is, does height differ between these two experiments? Maybe we set them up to be a replicate, but after we did our second experiment, we noticed that the heights appeared different. So we're asking, hey, are the heights the same or are they different? If they're the same, then we can kind of pool the data together as one large group. But if they're not, then we better keep them separate. That's the idea. All right, so go ahead and read in these data. They're posted on Blackboard. So I'm going to go back up to the start. Import data set. Yep, R did it correct this time. You to check that heading box. I'm going to make sure I check strings as factors as well. I want to say that, let me just move this over here. So when I read it in, it had it correct, it gave me the heading, but, X1, I have the strings as factor box checked, and I think we've encountered this earlier in the class when we demonstrated making some of the figures. This was a change in version 4. I started noticing that the factors weren't being read in correctly. They weren't being read in as factors, so then when we tried to do like the box plot or just the plot function, it would fail and say, you need factors. So just make sure that's checked. And then when you import, I get my code, copy it, and I'm going to put it in this top one. So I created a chunk right at the top of my markdown document, so I have it. All right, so it's in there. So we measure the height of plants in 2 different experiments. We are interested in testing if the heights differ between them. So we should recognize we've got 2 variables. We have a continuous variable and we have a dependent variable, or a continuous variable that's dependent is the dependent variable, and then we have a grouping level. So in our global environment, I could see it as this. 1 variable is listed as factor with 2 levels. That's good, 2 levels. And then I have a numeric variable that's going to be height. So far, it looks like everything's going to be set up correctly. I look at my cheat sheet, and it says 2 variables. These are the test options for me. T-test is going to be one of them. All right, so we know we want to run a t-test. We're going to assume that all of our assumptions are met, so we can introduce the t.test function. We've already had the t.test function. We did it for 1 sample test, right? But just like the QQ plot, t.test function has the ability of taking a formula. And we set up the formula as y is a function of x, where y is our dependent variable, x is our independent variable, and then we specify the data frame where we will find these variables. And there's one more option, and it's called var.equal equals t. So that option is, should we assume that the variances are equal? Yes or no? If we assume that they're equal, then var.equal is t. If we assume that they're not equal, or if we tested it and realized and determined that they are not equal, then we would use var.equal equals false. All right? So let's get our t-test. We have all of this. Yep.
After QQ plot, height, and then the thing, test, and then the X1 for the data, I put var.equal equals t, and it like didn't work. But if I don't have that part in there, then it
Why would you put var.equal equals t
I don't know. When do you
in a
use that?
QQ plot function?
I don't know. Yeah.
Right?
Yeah.
Wrong function.
Yeah.
Wrong function. All right, so I'm going to go back up to this 2-sample t-test. This is the introduction, right? We've got all of our information here. We've got our reporting. All right, the R code that we will use is t.test, y is a function of x, data, and then var.equal equals t. So the default is that var.equal equals t. So y, I already have this down here. I'm going to copy this from the QQ plot stuff since I've already written it. So y is our measurement variable, x is the grouping variable, data is the data frame where we can find x and y, and then var.equal equals t. Variances are equal. If var.equal equals f, variances are not equal. And this, when we do that, we'll actually perform Welch's t-test. And we'll talk about it. So when we're getting to that point where we have to address what to do when we violate assumptions. So if we're normally distributed, but we have unequal variances, this is what we do. Changes a test, it's Welch's t-test at that point. But this is how we approach it. All right, so got that. Here's our example. So our example was plant heights, right? We grew plants into experiments and measured their height. Question: are the plant heights different between the experiments? All right, that's our question. So our null hypothesis is that x bar 1 is equal to x bar 2. So our mean of group 1 is equal to mean of group 2. And our alternate is x bar 1 is not equal to x bar 2. Right. For this one, we are going to assume that all assumptions are met. We don't always do that, and we should probably never do that. But at this point, we're introducing the t-test. That's what we're introducing right now. So we're going to assume that all assumptions are met so that we can perform this t-test. So now we're going to run the test. And it's t.test. That's our function. Our measurement variable is height. Our grouping variable is test. And the data is ex1. And I'm going to use var.equals t because it's our default, but I like to always specify it so that I can quickly determine that we are running a regular two-sample t-test. I might not always remember that, but I might not remember what the defaults are, so might as well specify it. And when I run this, I get this output. So the output tells us what we just ran. We ran a two-sample t-test. Right? A t-test is sufficient when we report the name of the test. It gives us our t-test statistic. So the average difference in our means is negative 2.456. Our degrees of freedom, 48. How did we get 48? We took how many values we have in our vector, in our measurement vector, and we subtract by 2. That is the same as saying the number in group 1 minus 1 plus the number in group 2 minus 1. And then we have our p-value. Tells us our alternate hypothesis. Basically, we're running a two-tailed test. It gives us a confidence interval. What is this confidence interval of? What do you think it is? What is this t-value? 95% confidence interval is representing our difference of the means. So in our one sample test, it gives us our mean of the groups, and then it gives us a 95% confidence interval of that mean. Here, we can look at these two values and come up with the difference of the mean, and this 95% confidence interval is confidence interval of the difference of the mean. So if we belong to the same group, same population, that difference should be centered at 0. And then we have just random chance of being above and below and so forth. That's what this confidence intervals represent. And then we have the means of each of our groups. So what values are we interested in? Our test, which is reported as a 2-sample t-test. Our test statistic, that's reported as t equals negative 2.456. Our degrees of freedom, that's reported as df equals 48. And our p-value, which is reported as p-value equals 0.1772. 0.01772. So now that we have this, we can do a write-up. So before we get to the conclusion, I'll do the test statistics since we've already laid everything out. So we have a t-test, that's what we ran. Our t observed value is negative 2.46. Usually our test statistics round to 2 decimal places. Our degrees of freedom is 48. And our p-value is less than 0.02. Yep. I was, yeah. So you have the output on your screen so you can see it, and it should be the same as mine. That leaves us with the conclusion or the interpretation. Because we wrote the test statistic, degrees of freedom, p-value. That's 4. We need our last one. So what's our conclusion here? What's our conclusion? Okay, reject what? Yes. What do we reject? Null hypothesis. We reject the null hypothesis and conclude that the means are not the same. Right? Yeah. We reject that null hypothesis. But I don't like saying we just reject the null hypothesis and leave it at that. We actually do our conclusion and go back to our basic biological question, which was, are the plant heights different between the experiments? Yes, they are. So the experiments, or the plant heights, differ between the 2 experiments. That's our conclusion interpretation, and we have all of our reporting of the actual test itself. Not bad? Not bad, right? All right. Practice. Raspberry.csv. We counted the number of fruit produced by raspberry plants at the end of the growing season. We used Miracle Grow as fertilizer for 1 row of plants. Second row of plants, we used an organic homemade fertilizer. So our question is, did the type of fertilizer cause a difference in fruit production? So what I want you to do is read the data into R. I want you to, don't check the assumptions. We're going to assume that they're all right, and we haven't really addressed, other than doing the QQ plot, we really haven't addressed how to test for equal variances yet. And then I want you to do a write-up. Have your write-up of that. Have that for Monday. So we'll come in and we'll do some Z-score tests and t-tests as a quiz, and then we'll get going with this. All right.
When is homework time?
Did not. What did you do? I don't even know what homework now.
It was over the one.
Let me look at it. Can't remember if I posted another homework too. I did. So homework 9 was it? Hold on. Oh yeah. So homework 9 we had. I should do this. We had this the paper handout, and then we use that. You can look at it, and that was what that mini quiz was. And then, yeah, the one sample test. I think did we put that on like Wednesday maybe?
Yeah.
Yeah, I made an assignment where you can do it in R and you can upload it. So you can have those. I'd upload them by Monday because we did things by hand. This one sample test. This is kind of what we're going to have on the quiz. This one for homework number 9. Number 10, you can work on that on Monday in lab. You know, when we're done with the lecture, because our next quiz we'll be doing this, where I'll post it. I'll post a data set, and then you'll test. You'll run your t-test and make the conclusions on those.
Okay.
So, yeah, if you get this up on Monday sometime, but know that this is what our quiz is going to be on.
And
Okay. Yep. So what I will do is actually make a Blackboard announcement. I don't even know if I can put something on a calendar that says the quiz. I guess do others have that? Or that they go on the Blackboard calendar and say exam day? Or does that only appear if it's like a Blackboard quiz or something like that?
Never use,
That's it.
never use the calendar of Blackboard.
A couple of the students I know do. Yeah, homework 10 will be due on Wednesday. I think what we'll probably do is do a quiz on Friday then. So that way, if you have questions on homework number 10, you can ask on Wednesday, and then hopefully you'll be prepped for that quiz on Friday. And it's all just about giving you more practice so that you get to do this type of stuff before we get to the exam.
And then another question is when will we get our exam grades back, or are they already?
They are not posted yet because we had flight delays due to weather and pilot shortages. She made it back.
Okay.
So-
Yeah, I was like, I saw
Yeah,
her. I saw her in the UC, and I was like, wait.
I was gonna pick on them because Dr. Ope said they made it back at like 4 a.m.
Oh.
on like early Wednesday morning, maybe.
Oh.
Then I was gonna say, well, yeah, she should have been in my class on Wednesday. She made it, just blew it off. But no, yeah, that's the horrible. Dr. Ope, students can tell you all about it. I read Dr. Ope's email. Just